There's live chat on this thing.
Any trolls in the live chat who are just typing?
So that the inexistent people who are viewing this can ask questions on the go. Yeah, math is a game. That's awesome. Anyway.
We will eventually use this stuff to devise strategies for Fortnite or something.
Fuck Fortnite. Anyway. So last time we saw that the space of vector fields is, for every vector field, can be identified with the corresponding Lie derivative, and we saw how to construct these Lie derivatives acting on tensors via Willmore's theorem, which guaranteed that there exists a unique tensor differential operator that coincides with Lx on C infinity M and on the space of vector fields. But like the construction of that wasn't very geometric. It wasn't very well intuitive. For the most part, it wasn't even very constructive. So we'll look at a more geometric interpretation.
Just to remind myself, so this told us that the Lie derivatives were all the derivations on the tensor bundle?
What do you mean all?
Any derivation on the tensor bundle is Lie derivative?
Yeah. Yeah. So we look at some geometric aspects of Lie derivatives, which makes it clear what these Lie derivatives acting on higher rank tensors are. So suppose we have a vector field x in xm, and we have a corresponding flow box of this vector field at a point P in M. And let T be a tensor of rank R comma S. Whoops. The T's and gammas confuse me. All right, so let T be a section of the R comma S tensor bundle on M, and the proposition is, and we define T lambda by taking T, evaluating it at U alpha, and then flowing it back, so pulling it back under this diffeomorphism lambda. So equivalently, this is F inverse lambda. So the inverse diffeomorphism pushed forward, acting on T at U lambda. And this will be an element of the section of the tensor bundle on U. So F lambda is this flow diffeomorphism from U to U lambda. So now let's say we fix some point P, and we have the map that takes lambda and spits out T lambda of P, which is defined here, and is an element of the Rsth power of TPM as a vector space. And this defines a curve in this vector space TRS of TPM that passes through TP, of course. Since lambda equal to 0 is naturally a point on this curve. And then we have the Lie derivative with respect to x of TP. is equal to the derivative at lambda equals 0 of d lambda of p. So the idea is that for some vector field x, you'll have some sort of integral curve in the manifold. There's a vector space here which corresponds to this. Let's say you have an element of the tensor here. You can push for you can push forward this tensor along this flow to somewhere here, and then pull it back to get something else here. And the variation of this tensor in the space at this point will define the Lie derivative under that vector field x.
So this is like a commutative method, like going forward and driving back or something?
Yes. Yeah. So this is so. Oh, sorry, I said this wrong. You're not pushing this forward along here, but if you have some sort of tensor field, the tensor field will have some elements at every point. So you take the elements at two different points somewhere along the flow, pull back its value at this point over here, and you'll get something else. And you see how that changes as you flow along the curve with this parameter lambda. That's what this is doing. So you're taking t, evaluating it at the flow, evaluating it at the point where p goes after lambda time, the point that p flows to after lambda time, pulling it back, and that's t lambda, which is an element of this. And then differentiating this with respect to lambda gives you the Lie derivative.
So Arnold has a great description of this. He called this fisherman. There's a fisherman who sits at one spot, but the river flows past him, right? And the river carries like tensor fields. But he sits at one point and he like measures the tensor field at the same point over time. And he sees how that value changes, and the velocity with
Yeah.
that changes.
Yeah, that's that's one hell of a way to explain it. Mm-hmm. All right. So we prove this. So we start with t lambda of p is defined. This is just saying that this is the differential of the inverse of the diffeomorphism to the rs power acting on t at f lambda of p. This is just this statement on at the point p. We define theta x as an operator on gamma rs of m by theta x t of p is equal to d by d lambda acting on lambda equals 0 on d lambda of p. And we'll show that this is basically equal to the Lie derivative. All right. So it's easy to check that theta x is a linear derivation, since you can compute its local representatives, and those are linear derivations. It is also local because it's defined locally. And furthermore, theta x acting on the Kronecker delta tensor is equal to d by d lambda at lambda equals 0 of f star lambda delta, the pullback. But the Kronecker delta tensor is defined as being invariant under these pullbacks. So this is d by d lambda at 0 of delta, which is 0, because it's just the identity map on every point in the tangent space. So this implies that theta x is a differential operator. Now, because of Willmore's theorem, we only need to check that theta x agrees with the Lie derivative on smooth functions and on vector fields, and that'll guarantee that it agrees with the Lie derivative on every tensor field. So for f in C infinity m, we have f lambda defined that way is nothing but f composed with the flow. d by d lambda at lambda equals 0 of f lambda of p is then from this is going to be the differential of f composed with d by d lambda at lambda equals 0 of f lambda, and this by definition is x. So this is df composed with x, which is nothing but the Lie derivative of f by definition. So we've checked that this agrees for scalars. Does this make sense? Or are people already lost in the notation? Okay.
Is it clear what they want to prove?
So I guess my question from earlier is, do we find differential operators which satisfy all these conditions that can't be expressed as a linear? I think this is sort of off
No, we don't. We define this differential operator like this, and when we want to show that it's the Lie derivative acting on the tensor.
But once we've shown it's a differential operator satisfying these properties, can we be sure it's which property? That is a local linear derivation.
Yeah.
Rank preserving derivation of the tensor bundle.
What preserving?
Or that it matches tensors in the same rank, tensors in the same rank.
Mm-hmm.
Are they all derivatives with respect to some vector field?
No, of course not. Covariant derivatives.
Yeah, exactly.
Okay.
So that's what we're trying to show now. So we're going to show that this is a Lie derivative, which is the whole point. And to show that this is a Lie derivative, it suffices to show that it acts like a Lie derivative does on scalar functions and vector fields. So we've already done that for scalar fields. We do that for vector fields, and then by Willmore's theorem, which we looked at the last time, the way we constructed tensor differential operators, it'll guarantee that this is just going to be the Lie derivative of on any tensor field. Right. So for proving the same on a vector field, we first note that for some function on M, there always exists a function g lambda parameterized by this lambda that is also smooth, such that g0 is the Lie derivative of f, and f composed with f lambda, which is this f little lambda, is going to be f plus lambda g lambda. In particular, lambda g lambda of p is going to be integral 0 to 1 dt f composed with f t lambda at t dt. There's just another way of saying that this is going to be the derivative, the lambda derivative of f lambda. Just if you rearrange this, lambda g lambda is just f lambda minus f. So g0 is nothing but the lambda derivative of f at lambda equals 0. So it's a difference between the value of f at lambda and the value of f at 0 divided by lambda. Right. Okay, so now for another vector field, y, we look at this Lie derivative theta xy f of p, and we'll show that this is nothing but the commutator of the Lie derivative with respect to x and the Lie derivative with respect to y, which will guarantee that theta xy is the commutator of x and y. Right. So this is, I'm going to write a new column.
That's how we define the
Of vector fields.
vector fields. So we use with respect to the feature, the commutator of x and y equals the commutator of feature with respect to x.
Yeah.
Yeah, this is the Lie derivative of us.
Yeah, exactly.
So we need to show that this Lie derivative equals the commutator of those.
So if we can show this, this would imply that theta x y is equal to x comma y, which would imply that theta x is nothing but the Lie derivative of y with respect to x. So L theta x y acting on f of p is equal to df composed with d by d lambda at lambda equals 0 on f minus lambda, the inverse flow, pushed forward at p, composed with y evaluated at f lambda of p, just by that definition. And this is d by d lambda. So this df can be pulled into this, and lambda equals 0 of f composed with f minus lambda, and then pushed forward, composed with y, and y being evaluated at the point f lambda of p.
So that's basically chain.
Yes, exactly. Furthermore, this is d by d lambda at lambda equals 0 of this.
We're dropping, so df, strictly speaking, is the second projection onto the second component of f star. Okay.
Yeah.
We're dropping the projection.
Yeah, exactly. And then and then this thing, we defined g lambda according to this. So f composed with f lambda is f plus lambda g lambda. So this thing is going to be f minus lambda g minus lambda composed with y composed with f lambda of p. Oh, with a push forward here. And because this derivation and composition are all linear, this is going to split into two terms. So we have the first term, d by d lambda at lambda equals 0 of f star composed with y composed with f lambda of p minus d by d lambda. So when this d by d lambda acts on this term, we can use chain rule on these three terms, but every time d by d lambda hits g or f, there's a lambda outside and we're evaluating at lambda equals 0. So those terms vanish. So we'll only have d by d lambda of lambda times g minus lambda star composed with y composed with f lambda of p. Yes, at lambda equals 0. So we evaluate the first one. This can be written as d f star composed with y, and then composed with d by d lambda at lambda equals 0 of f lambda of p. That's the first term, which is basically doing the reverse of that here, of what we did on the first line. Yeah. Minus d by d lambda of lambda is just 1. So g0 star composed with y composed with f0 of p. Now look at the first term. D by d lambda of f lambda at lambda equals 0 is the vector field x. So this is the x Lie derivative of the y Lie derivative of f.
F star y is just
Yeah.
Ly.
So this is Lx Ly of f, the first term. And the second term is, so y acting on f0p is, yeah, f0 is just identity. Wait, what was g0 star? Right. So g0 star was, where do I see that?
There should be a function somewhere.
There should. No, the function is in this. Yeah, within G. Right. So G minus lambda was defined as this f minus lambda minus f0 divided by lambda. So taking the limit lambda going to 0, G0, and pushing it forward, this is just going to be the Lie derivative with respect to x. Does that make sense? All right. Yeah. So this thing is Lie derivative of f with respect to x, and then composing it with y is going to give Lie derivative of y, Lie derivative of x of f. Is that clear? So this is just the commutator Lx, Ly on f. So we have theta xy is equal to x comma y.
The reason this implies that theta xy equals commutator of xy is because we know that the space of theta is x margin to the space of
Right.
derivation.
Exactly. To the space of vector fields. Yeah. Yeah. All right. So we have this, and this implies that this is nothing but the Lie derivative of y with respect to x. So theta x is equal to Lie derivative of x on the space of vector fields. This looks like an H. All right. So we have shown that theta x agrees with the Lie derivative on scalar functions and on vector fields, which means that it has to be the Lie derivative on every tensor field. All right. Questions about this proof? If you followed this, you'll follow every other proof in this talk. All right. I'm going to move on then. Okay. So we have a couple of corollaries. Firstly, the Lie derivative of some tensor field with respect to a vector field x is 0 if and only if t is constant along the flow of x. That is f star lambda t is equal to t, because the Lie derivative is literally defined as d by d lambda of this. So if this tensor field is going to be constant, its derivative will be 0, and you can also show the converse.
So we have, so when we have some chosen vector field, and we automatically get the notion of comparing tensors at different points.
Yes.
Just by transporting them.
Lie transporting them. Yeah.
Okay, so this gives us a sort of limited prescription for parallel transport.
I'll talk about that in a minute. Yeah. Sort of. But secondly, for all lambda in the flow domain D, yeah, 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 exactly. Yeah. Right. So
Explain this to you why we transport is not covariant transport. It's not parallel transport.
because
Didn't
well, you explain why Lie derivative is in the covariant derivative. So like this Lie transport not being the parallel transport is the next remark after this corollary. So I'll get there. So if you have for any lambda in the flow domain, you also have d by d lambda of f star lambda of t is equal to f star lambda the derivative of t with respect to x. This is just the chain rule. In particular, you can write the Lie derivative of t with respect to x as the following: f star minus lambda d by d lambda f star lambda of t, which is nothing but d by d lambda at 0 of f star lambda of t. So this formula sort of makes it clear what you're doing. You're taking this tensor, you're pulling it back by lambda, differentiating it, and then pushing it forward again.
And this is, by the way, it's important that the formula is true, not going for lambda equals 1.
Yeah. So this first part, it's valid for any lambda.
It's just that lambda equals 0, it's
So a remark, because we've computed this geometric version of the derivatives, we also have that push forwards, when they're well defined, are equivalent to transport under Lie derivatives. Or transport under the flow of a vector field. However, this is not equivalent to parallel transport. Because Lie derivatives and covariant derivatives are very different, because covariant derivatives have to be C infinity linear while Lie derivatives don't, and in fact they aren't. And secondly, suppose let's say you pick some curve in the manifold and you want to transport a vector at some point on the curve to some other point. If this transport is parallel transport, it's supposed to be unique. There's only one way to transport this vector depending on the curve. But there's infinitely many vector fields with this curve as its integral curve. And the corresponding Lie transport along those vector fields will all give you different results.
So if we reparameterize our paths,
Mhm.
we get a different Lie transport. Is there a way to become faster?
Yeah, exactly. Exactly.
Is there an easy way to see that from the way we from this prescription for retransporting tensors?
Well, this only defines a Lie derivative. Lie transport would be sort of like exponentiating this, because the Lie derivative is infinitesimal Lie transport. Yeah. So then, depending on how you parameterize that curve, the exponentiation will be different. All right. So that was a remark. And then we have another remark in order. Suppose you have some partial differential equation in Rn of the form, some linear partial differential equation of the form del t x, del t of f is equal to sum over I from xi of x, del I of f of xt. Well, actually, this doesn't have to be linear. And initial conditions f of x comma 0 is g of x. All this Lie derivative business gives us a way to solve this. And by treating xi's as the components of a vector field on Rn, and then if this vector field x has a complete flow f sub t, remember that a flow is complete if the flow domain is all of m cross r. So you can keep flowing for all values of time, going all the way to infinity. It doesn't truncate after a finite amount of time, and yeah, that's basically it. Right. So then you have a unique solution to this Cauchy problem, given by right. F of x comma t is g of ft of x. So you flow the point after time t under this, you push the point forward under this flow for time t and then evaluate g at that point. And one can check that this solves the differential equation just by direct substitution. This is called the method of characteristics. where these characteristics are basically defined as integral curves along which the values of g are propagated. Right. Yeah.
No, but it's linear. What? They don't act on fields. So now equation will have two times. So yeah, but split into chiral sectors are restricted like one drift. So like a dx. This will be d by dx plus minus d by dx.
Exactly.
Then what are characteristics? Like minus vt next or whatever. Yeah, so for every point, they're just curves that go like that.
Yeah.
And these curves describe the propagation of this. We know. So they're just lines that
Yeah.
the Cauchy problem is exactly solved by that.
Like the solutions are of the form x minus vd, and that's what this is telling you.
okay, good. So more generally, this converts PDEs into what, a system of ODEs you solve to get the characteristics, or what does this do for us?
It doesn't have to be a system of ODEs. Oh, yeah.
But system of ODEs with variable initial conditions.
Just determine by this.
It's the same as Hamilton Jacobi variance.
Hmm.
Only that's not linear.
Yeah. Yeah.
Hamilton's principal function.
Yeah, exactly. All right. So we're going to have a proposition. Suppose x and y are two vector fields on M with complete flows ft and gt respectively. And then the following are equivalent. Number one, x commutes with y. Number two, f star dy is y, or g star dx is x. So the second statement means that x and y are invariant under each other's flows, if and only if they commute with each other. Third, ft composed with gs is equal to gs composed with ft. So the order of flowing along either vector field doesn't matter. You can flow along one of them and then flow along another, or do the other way around. For all t comma s. And finally, finally, in particular, we also have the flow of the vector field x plus y, is given by, which is given by ft composed with gt, which is well defined because f and g commute with each other. It doesn't matter what order you take them in. You can think of this as justifying the parallelogram on real space, parallelogram of law of adding vectors, but don't want to do that.
And for x and y that don't commute, you have to use some type of Baker-Campbell-House
Hmm.
to find the flow x plus y.
Right.
You kind of commute them and come back, and there would be like some mismatch.
Exactly. Yeah. Yeah. All right. So proofs of these statements. So we first prove that 1 implies 2. So we have d by dt of ft star y. So we'll prove that 1 implies 2 by computing the derivatives of both sides of the second equation and showing that they're equal, and then the initial values are equal, which means that the functions have to be equal themselves. So this is by definition, by an earlier proposition that we saw, ft star, the pullback of the Lie derivative of x acting on y. Now the Lie derivative of x acting on y is just the commutator, which is 0, so this is also 0. So f star t y is constant because its derivative is 0, and at t equals 0, f star 0 of y is just y. Therefore, f star t y is y for all t. And then we prove 2 implies 3. So we have d by dt of ft. So we'll prove this for t equals s, but it's very easy to generalize to just general variables. Composed with gt of p is, once again, x of ft of gt of p. This thing is the Lie derivative with respect to the vector field of f of this value. No, I am. Oh, I should write that. Plus f t star y of gt of p. So it's chain rule. And then the hypothesis implies that this is equal to y. Yeah. Right. So this thing is y evaluated at f of t of g of t of p. So you can just add the two, and this is x plus y of ft of gt of p. Way too many brackets here. Or let me write this. It's ft composed with gt. And you can do the same for gt composed with ft as well, just by reversing the order. And that'll give you a y first, and then an x, and then x plus y is the same as y plus x. So you'll get the same thing. Oh, yeah. Yeah, so you get x plus y at, what's it called? gt composed with ft of p. And then at t equals 0, the derivatives are identical. Wait, no.
You're not proving that 2 implies 3 right now. You're proving that the flow of x plus y is the composition.
Oh, right. Yeah. So the d by dt of this thing is x plus y acting on this, which by definition means that the flow of x plus y is the composition. All right. Yeah, we've shown that the flow of x plus y is ft composed with gt. I didn't. No. Wait. Yeah. Wait. How do you prove that ft and gs commute?
Differentiate with respect to t separately and with respect to s separately.
Oh, right.
So you run the same argument, but now the second term vanishes if we type out as s, for instance.
So for 2 implies 3, you compute d by dt of ft composed with gs.
Which is what you just did without the second term.
Yeah, exactly. So that is going to be x d by ds, like well, if you do the same on the right hand side, you're still going to get the same thing. So the two of them are equal. They are equal on the same initial value t equals 0. Yeah, exactly. So for the second one, you get this, but that is, let me just write that down. This is going to be x f t gs of p d by dt of gs composed with ft is going to be ft star no, gs star x ft of p, and this is nothing but x by the hypothesis. So this is x composed with gs. So this is x gs of ft of p. Wait, but these are still not the same.
No, you need to use the fact that G star is minus 1.
Yeah, so we also need to differentiate with respect to s.
Right. No, so like I thought you would. I thought we had to do this separately for the t derivatives and s derivatives. Like show that the t derivatives are equal, which means that they're equivalent as functions of t, and then show that the s derivatives are equal, which means they're equivalent as functions of s. Actually,
But it's not going to work out. If you take the double derivative and prove that they're the same, then you're done.
the
I mean,
double.
by double derivative, I mean the next derivative.
Oh, I see.
Doesn't this just say that the derivative with respect to t of the flow at any point is x? At that point?
Say that again.
So this statement you have written down, regardless of order, the derivative of the flow at any point is x at that point.
Yeah, that's basically it.
So can we say the same on those grounds that there is some s and some p? If there is some s and some p such that we flow to the same point, the derivatives will be the same at that point?
No, but this completely tautological. This by definition.
Yeah, exactly.
So this is not containing any information. What you need to do is take d by ds of these two things now.
Right. So if I take
The second derivative and then the first derivative.
actually this should be a
Then the main derivative
partial
for PCH.
partial s partial t of ft composed with gs is partial s of x composed with ft composed with gs p, and this is going to be x and ft don't depend on
No, but you need to take that
yeah.
differential. And you leave derivative with respect to y, and you cross with respect to x.
ft. Wait, what?
You just proved the property of lead derivative.
Oh. Yeah, so gs. This is the derivative x composed with ft, so gs plus x circ the derivative of y, ft, circ gs plus x circ ft, circ. The derivative of y with respect to gs is just del by del s of gs, and that's y. Um,
Wait, that's meaningless. What are you doing?
wait, what have I done?
Yes, FT composed.
Oh, yeah.
Isn't it y composed with gs?
Right.
And what's FT composed with y?
That doesn't make sense. The derivative of y with respect to gs. Oh, no, wait, this is 0 because y is invariant under its own flow. So this term vanishes, and you have Lyx circ ft circ gs plus this is by our hypothesis is just y. Yes, x. This thing? Where would this be 0? Oh, this the lead derivative of the function. It's just a composition, right? Hmm? From the
Why do you even have that term? Oh,
just chain rule.
what chain? This thing just equals that thing, right? By the theorem we just proved.
Oh, right.
Up to maybe push forwards. So like you have to be
Yeah.
careful. The y that's here is not y. It's really f star y, right? Because there's an f in there.
Right.
And at this point, now you say we use the hypothesis, and it's Lyx computed on that.
Right. Okay. Yeah. Never mind. Right, and you also have del by del t if del by del s of f gs circ ft is equal to del by del t of x circ gs circ ft. Now this hits here, and this is just going to be the derivative of g star x. Oh, wait, no. I'm very confused by this. G star x of x. Does that make sense?
What are you doing right now? Differentiating with respect to
This thing with respect to wait, what am I doing? Oh, that's why. Yeah. Okay. Yeah. So this is once again.
immediately just y. So this is just vy.
Yeah. Ey of x composed with gs ft, and this is well what we had before. So del by del s, del by del t of ft composed with gs. Right. So the mixed partials. Hmm? No. So like, take these two functions. Their derivatives are identical. And if you look at the initial conditions, they're identical as well, which means those functions.
You didn't check the proofs, right? They're equal to Lyx at different points.
Oh, right.
Is the way to do this to just start with Thoreau's theorem and say we can switch the partial derivatives for free and then get two different expressions? Or what happens when we differentiate the other way?
One sec. It's turned out to be more complicated than I thought. Wait, what if I take like the s derivative here? Del by del s of gs circ ft. It's going to be y of gs circ.
Does it just give us something trivial if we use the top expression in the next word and then write it equals the same thing but with the derivative swap and just expand it?
So you're saying del by del t of del by del s of the first expression. No, but that still doesn't relate like ft composed with gs to gs composed with ft.
Continuing exercise.
Yeah. Never mind. Whatever. All right. We have a definition that of a holonomic frame. What was 3 again? Yeah. Oh, right. So yeah. So to prove 3 implies 1, we'll split this into 2 parts. We'll prove 2 implies 1, and then 3 implies 2. I should probably write down 2 and 3 again. 2 was that f star ty is equal to y, or g star sx is equal to x. And 3 was ft composed with gs is equal to gs composed with ft. Maybe even 1. So 2 implies 1 is simple. Compute lxy, which is just the commutator, by using this formula, f star minus t, d by dt of ft star y, which is what we proved in a proposition earlier. And this is just y. So this is f minus t star d by dt of y, which is 0. So x commutes with y. For 3 implies 2, f d star of y is, since y is nothing but the derivative of its own flow, d by ds of gs, which is ft star gs star of y. Actually, you don't even need this middle step. Y is going to be propagated to itself under its own flow. This is ft composed with gs star of y, which by our hypothesis is gs composed with ft star y, which is gs star ft star of y. So ft star is propagated to itself under flow by g, but the only such vector field that is possible is y. The only vector field that remains invariant under its own flow is under a flow is the flow that is the vector field that generates the flow, which implies that ft star of y has to be equal to y. Yeah. Yeah. All right. So we have a definition. Of a holonomic frame. So a holonomic frame is a local K frame, which is a set of basis vectors for the tangent space such that all the basis vectors commute. And then we have a theorem called rectification of frames. Yeah. So suppose Ej, j equals 1 to k for k less than equal to m, which is the dimension of your manifold, is a holonomic local k-frame. On some open subset of the manifold. We assume that the basis at a point P is such that it lies in the, well, it's orthogonal to the tangent space of some embedded submanifold transversal. Yes. Yes. There's no inner product yet. Yes. Such that the codimension of this manifold is K. So you have this embedded submanifold of M at and at a point P, its tangent space is a K minus M dimensional vector space, and the basis spans whatever is not in that tangent space. The statement is that there exists a local chart in which S is given by S1 equals S2 equals dot dot dot, Sk is equal to 0. As well as EI is given by del I in that local chart. So this tells you that a holonomic local frame that's always everywhere transversal, transverse to an embedded submanifold can be is a coordinate frame. It can be written as del by del of some coordinates in a local chart. We have a proof. So we parameterize S as usual. By coordinates x from some omega into S for omega an open subset of R m minus k, which is the dimension of S. We're working locally, so it suffices to just think of some batch. We define a chart on this patch phi. Oh, writing too fast. As psi inverse, where we define psi as a map on Rm that takes in S1, S2, dot dot dot, Sk, followed by Sk plus 1, Sm, and spits out Fe1, S1 composed with dot dot dot, Fen, Sn, x of Sk plus 1. Oh, right. So it takes an arbitrary point in Rm in the corresponding patch for the manifold, takes the last last k minus m minus k elements of it, maps it into the manifold through this X through the chart for S, flows those points where F E I S I is the flow of EI. So flows those points along these holonomic frame directions for the values given by these S's. And that's the inverse of and that's how it gives a point in that's how it gives a point in S. Or
The idea is to parameterize points from this using
Yeah.
the times that it takes to flow to that point along these.
So S here is everywhere.
by our assumption.
Okay.
So like this basically the reason that is important is because if it wasn't, then you'd have a flow that's restricted within S, and that would essentially create issues. You wouldn't get a unique parameterization like this. And this is well defined because the frame is holonomic, so all of these flows commute with each other.
So I was wondering about EI partial Y.
Uh-huh.
So those partial those EI, they don't ever exist in X, right?
No, but so they don't exist. So S is given by these coordinates being 0.
Okay, sorry.
So it's the other k minus m coordinates that form a chart on S.
Yeah.
But you also have these, and in these directions you'll still have a derivative basis for the tangent space of M. So TPM is the span of
So aren't EI only defined from
del 1 all the way to del k, and then del k plus 1 all the way to del m. So these span the basis of TP. These span TPS, and then you have these which are going to be EI.
Okay. So we're constructing a chart not for S, but for all of
Right. Yeah, for a neighborhood of M.
Such that only some of them coincide with.
Exactly.
But and then our directional derivatives would just be somewhere effective our choice of parameterization in the transverse space.
Some say that again.
Because we're just parameterizing the transverse chart or the transverse submanifold for we want.
No, can you repeat the statement? I missed that.
Or so this transfer everywhere transverse submanifold S.
Mhm.
Just choosing some parameterization for it.
Yeah.
Okay. And so there are partial derivatives will just be as they are.
Yeah, exactly. All right. Yeah, so because all of these flows commute, sine inverse is well defined. And then we compute the partial derivatives. By considering psi star, the push forward of del Si acting on F for some test function F. This is going to be del I of F composed with psi by definition of push forwards. Psi is this. So this is del I F composed with FE1 S1 dot FEK SK times X of 0, 0. Let's say we set the first uh, the first k values to 0, and then we have sk plus 1 all the way to whatever, all the way to sm. Now we just use chain rule on this. So this is going to be del I f ei si, the remaining f's evaluated at 0, 0, sk plus 1, and all of these. This is just by chain rule. And this, by definition of f, is ei. and whatever remains is just f. So there's ei times f, which is equivalently the Lie derivative of f in the direction ei. And so the del SIs are a basis on Rm or Rk. So you need to push them forward to get a basis on this manifold. So this is essentially equal to this, which implies that ei is del I. Right. Is that clear?
And that's how we define our
Pretty much.
So Rn generally, this Euclidean basis has this property that flows commutely. So
Exactly. So we define Rn as something where flows commute.
I'm guessing it's somewhat special that when we define parallel or like the VGB of parallel transfer, they're the same.
Can you say that again? In Rn, yes. Yeah. A corollary, so we can reformulate this statement for k equals m as follows. A given local frame is a coordinate frame for some local coordinates meaning the given frame ei is some del I for some local coordinates if and only if it is holonomic. So if all the basis elements of that vector field commute of the frame commute, then it's going to be you can write it as some coordinate frame at every point on a patch. Yeah. Exactly. All right. So the main topic of today is Frobenius theorem. Recall that a distribution
The Frobenius theorem is actually the analog of this corollary for k less than m. The question is like, if you have a holonomic k frame, what can you construct out of it? Like, what type? You know, you don't have a local coordinate chart on which that frame is the coordinate vector fills with. Maybe there's some tangent, some manifold.
Exactly.
Because it's a smaller frame, right?
Yeah.
Can you, in general, construct a holonomic frame from a given frame? Or I guess is there some analog to like the Graham-Schmidt process? So if they don't commute, can you combine them in some way? Yeah. Like Graham-Schmidt was said they had a commuting subset. Yeah, or like subset of commuting linear combinations.
Well,
It's unclear.
I don't think that's
but
true.
it wouldn't be so simply algebraic.
Yeah.
Yeah.
No, I mean, no, but if it was, you'd get an integral manifold anyway, right? Like not all manifolds are integral, so not every frame can be made
He's saying
holonomic.
you can combine them with some functional coefficients and get.
Oh, I see.
That's true. But define those coefficients, you need to solve differential equations.
Well, I guess we can always be sure the local chart exists, so it's not like they're never going to line.
All right. So recall that a distribution D on a manifold is an assignment of subspaces dp of dp of m for all p in m if dimension of dp is constant, call it k, then D has rank k. If D is a subbundle of Tm of the tangent bundle, then D is a smooth distribution. So given a smooth distribution, we can define something called an integral manifold of the smooth distribution. Yeah. The integral manifolds are essentially the high dimensional analogs of integral curves of vector fields. But the integral manifold for a smooth distribution is an immersed submanifold. I'm writing that. N of M.
You wrote it twice. Come on.
Yes.
I like writing things twice.
I like writing things twice. Every time I look at this symbol, I'm like, what the hell is this? If dpn, the tangent space at a point P of n is dp for all P in n. But D is a smooth. I'm going to write this as well. Distribution. So if such an immersive manifold exists, it'll be called an integral manifold of the distribution. Of course, this is going to be somewhat like a local property. Well, not local, but like n does not consist of every point in n. Otherwise, this would just be trivial. But yeah. All right.
Just like integral curves.
Yeah. Another definition, which is that of integrable distributions. Guess what that is? Nobody? Pretty much. Well, slightly stronger than that. So if D is a smooth distribution, it is integrable if every point P in M is contained in a local integral manifold of D. Because the integral manifold, of course, cannot cover every point in M. But every point P must be covered in some sort of integral manifold of D. One more definition, then we'll go to the theorem. This is involutive distributions. Once again, D is a smooth distribution. Suppose gamma of D as a subset of chi M is the well, notation. This is the space of D valued vector fields on M. So such that the vector that the field maps into at every point must be an element of the distribution at that point. Then D is involutive if gamma of D is Lie subalgebra of X of M. That is x comma y is in gamma of d for all x and y in gamma of d. Not the yeah, exactly. Exactly. Exactly.
Why is it called evolution? Evolution makes me think you're doing something twice and getting the same thing back.
I
Why is the word evolution?
I think that
yeah. So like you take two fields and take their commutator and you get like in gamma d and you still stay in gamma d.
evolution means for some bracket equals
Oh, okay. I'm
Hmm.
thinking of like a linear algebra operator, something that squares together. Okay.
All right.
integral of motion in evolution. Integral is, in fact, that's just another version of it.
Yeah, pretty much. So we have Frobenius theorem, which says that every smooth distribution D is involutive if and only if it is integrable. Put this into a box. It's Frobenius theorem.
This is only the local for me.
Yeah.
But then you can make it stronger and stronger. You can study maximal integral. Just like with integral curves, right? You can study maximal integral curves.
Exactly.
And but it gets very messy very quick.
Yeah. So a proof, the backwards is sort of trivial because if D is integrable, it's equal to D integrable implies that D is the tangent bundle of some immersed submanifold locally. And of course, vector fields in a that take values in this tangent bundle are going to, their commutator is also going to be in this tangent bundle. Going forward is the non-trivial part. So for this, it suffices to prove that D is locally spanned by um, a holonomic frame. And then by rectification theorem, this would imply that this holonomic frame is a coordinate frame, and we have coordinate vector fields for a slice chart of the integral manifold. And then we can define the integral manifold through its slice charts, at least locally, and we'll have that D is integral. Furthermore, the locality of this statement implies that it suffices to prove this only for some open set of Rm. Right. So pick a point P in M, or just this open set of Rm. Um, we can find Cartesian coordinates. Such that dp is completely spanned by, oh, sorry, dp is, what's the symbol for transverse? Never mind. So is that dp is transverse to the span of these fields, k plus 1, dot, 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 del m.
Yeah, by the way, so just to note, to avoid confusion, in the last proposition we had the S, right, the manifold S, for which these E's were transversal. That's not the M that's going to be, that we need.
Oh, yeah.
Okay, absolutely. So S is not, the S in that theorem is not the S that we're trying to construct to get the submanifold. Right? If we're picking
Yeah,
the rest.
yeah, exactly. All right. So we found coordinates where Cartesian coordinates where dp is transverse to the span of the last m minus k basis vectors at the point P. We can do this because we're in Rm. By continuity, this is also true in some neighborhood of P. Therefore, we have a non-singular projection phi from Rm to Rk onto the coordinate hyperplane that spans dp. So the hyperplane of the first k coordinates. Restrict that projection to U, of course. So with the projection, we also have its push forward that we can restrict to the smooth distribution D. And this restriction will be a smooth bundle isomorphism. Because it's a smooth bundle isomorphism, we can consider pullbacks of the coordinate basis vectors for I equal to 1 dot 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 k, and these locally span D because we have a bundle isomorphism there. Furthermore, we can consider the commutator of these elements, and this is just going to be by the property of pullbacks, phi star, commutator of del I and del j, and del I and del j are coordinate basis vectors, so they commute, so this is 0. And since these locally span D, we found a holonomic frame for D. And since we argued that showing that D is spanned by a locally holonomic frame suffices to show that it's integrable, we have an integrable distribution.
This non-singular projection onto some coordinate hyperplane, right? And you just take the coordinate vector fields in that hyperplane and pull them back to cross section.
That's how we're getting the holonomic frame here.
Yeah.
Oh, that's cute.
All right. So that's the proof of the local version. For instance, there's one of the global versions says that that a distribution is involutive if and only if it arises from a regular foliation of the manifold. So it also talks about whether smooth manifolds can be foliated or not by looking at distributions. We have a remark. So we can have an overdetermined system of linear PDEs, and we can comment on the solvability of these by saying that they're solvable if and only if the distribution spanned by the differential operators as vector fields is integrable. So this is this historically why these distributions are called integrable? Because I know Frobenius theorem was first originally shown for with relation to partial degree. Yeah. Yeah. Exactly. Like a vector field is a smooth rank 1 distribution. Yeah. Yeah.
So this is kind of like in overdetermined systems of linear equations, like matrix equations, you have solvability conditions.
Yeah.
So like.
Yeah. So this system of linear equations solvable if and only if if and only if there exist these coefficients such that the commutator of these xi with xj is ckij times xk, and similarly xi acting on fj minus xj acting on fi is ckij fk with summation convention.
So basically, the linear relationships that exist between x's must be the same between the f's on the right. So it's literally the same solvability conditions like in matrix.
Exactly.
And the linear relationships are replaced by weak derivatives being in the same subspace.
Yeah. All right, so we start a new section now. Differential forms and integration. New chapter. Although we won't get to integration today. We actually won't even get, we won't even get to differential forms. So we have first the exterior algebra. Is it? Yeah. So an exterior form, well, if you have a vector space, you can define alternation and symmetrization maps. as on the tensor power of this vector space, the kth tensor power, as alt t is equal to 1 over k factorial sum over elements of the kth permutation group sine sigma t sigma, and sim t is 1 over k factorial sum over the permutation of t sigma without the sign, where t sigma is defined first on a basis, so that if I have ei1 tensor dot 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 ein, its action under this permutation will be will be e sigma of I1 tensor dot 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 e sigma of ik, and then extended to the entire vector to TKV bilinearity. Is there a basis independent definition of this?
If you refer to the dual space and you act on some arguments, and then you permute that.
Yeah.
In the context of vector spaces, do we like to decide what the even odd permutations are?
That's just, yeah, even in odd.
Even the identity is even.
Yeah. Yeah, exactly. All right. I could call it -1. So we can denote lambda kv as the set of, well, the set of alternating rank k tensors, and sigma k v as the set of symmetric rank k tensors. And exterior forms are elements of, well, they're literally alternating tensors of degree k. Furthermore, if dimension of v is equal to n, then the dimension of lambda kv is going to be n choose k. In particular, lambda 1v is nothing but v itself, and dimension of lambda 0v is equal to dimension of lambda nv is 1. So lambda 0v and lambda nv are basically the set of scalars, and right, yeah, it's isomorphic. Well, it's bijective to the set of scalars. Not really. And for any number greater than n, this is going to be 0. Well, some people do. All right. Ooh, there's more. So lambda k and sigma k are covariant functors from the category of finite vector spaces into itself. And they act on morphisms as lambda kf is going to be the alternation map composed with f tensor k, and sigma kf is going to be the symmetrization map composed with F tensor K.
So I thought about this, and I think it's actually redundant because if you take, let's say, an exterior form and you act on that with F tensor K, the result is already an asymmetric.
Yeah.
So like that alt is useless and that sim is useless. It's just F tensor K restricted to those subspaces.
Yeah. Pretty much.
I've only seen these defined as like basically subalgebras or tensor algebras freely generated for each, right?
No, but I mean, as a functor, it can act on any vector space, right? The vector space doesn't have to be the space of.
Yeah, he's not worried about sending objects to objects. He's worried about the morphisms. Right? I mean, he's saying the morphisms writing all through signals are done.
Oh, right. Yeah.
Sure, F tensor K preserves the symmetry.
Yeah, exactly. Yeah. All right. So, of course, for a basis, suppose we have Cartesian coordinates xi for the vector space V. We have a basis given by del xi, and we also have a dual basis for V star given by dxi, such that dxi acting on xj is delta ij. Oh, yes. Goodbye, Frobenius.
Whenever people say integrability, integrable systems of physics, right? Integrability of any kind of structures, like complex structures, etc. It's all just variations on in classical mechanics. Integrability comes from Liesel Arnold. If you have a two-dimensional phase space and integrals of motion in involution, like their flows can be or their flow apparatus. Then the motion is actually restricted to what's topologically equivalent to an undimensional force.
Isn't, yeah, that's,
This is the same statement as in the infinite differential case. If you have an integrable quantum field theory, then you need infinitely many inputs to motion. It's like this is the same statement that you have to find.
yeah.
Well, in the infinite differential case, it's not enough to just have an infinite number, right? Because you never know. Maybe you have half of the number that you need.
Yeah. It's necessary that you have infinitely many inputs to motion.
Yeah.
Yeah. Right. So if we have a basis for the vector space, we have a dual basis as well, and then we get a basis for the kth exterior power of V star, and that's given by these wedge products, which I'll define later. But essentially, they're just the alternating map applied to this tensor product, but only for the indices, so that I1 is less than I2, less than so on and so forth up to IK. If you have any other sort of ordering, it's going to be equivalent to this up to a sign. Yeah. So now we define a determinant, but this time the way mathematicians do.
We didn't know until now what the determinant is.
Yep. Yeah, actually. We knew determinant of matrices, but what the hell are matrices? So suppose V is a vector space over a field K. with dimension of v equal to n, and let f be an endomorphism on v, which is just fancy words for a linear map from v to v. The determinant of this map f is defined as lambda to the n of f. So just the alternation map applied to f tensor n. Well, in a basis, f would be a matrix, and this would be literally the determinant of the matrix, which we'll show in a minute. But in particular, this is an element of homomorphisms from lambda nv into lambda nv, which is identical to the field k. So is a well-defined scalar.
The homomorphisms from a one-dimensional space into itself. It's naturally, it's not just one-dimensional, it's naturally isomorphic to the field.
Yeah.
On a one-dimensional vector space, you can divide it all.
Exactly. Which is why, yeah. So this is then a well-defined scalar, unlike elements of lambda and v themselves. Is not what?
It is truly a scalar and not an
Yeah. Proposition. How much time do we have? All right. A couple of propositions. Dimension v is equal to n. If dimension v is equal to n for any t in lambda and v star, and any f in endomorphisms of v, the pullback of t with respect to f is going to be equal to determinant of f times t. This tells you that t is not a scalar, because this is how it transforms under pullbacks. Transforms with this determinant. What is this called? A tensor density or something? It's a tensor. This is, I don't know, never mind. And secondly, for f an endomorphism, oh right, densities are if they transform under a power of determinant. Yeah.
It's like epsilon or epsilon. Right?
Yeah. Right. Yeah. So for f an endomorphism represented by a matrix f on EI equals A J I E J in basis given by these EIs, determinant of f is going to be determinant of its matrix representation, which will be some whatever. Look at the all right. I'm not going to prove this. Maybe I'll prove the first one. The second one is just very easy, but just long. So if v is a top form, well, not a top form, but an element of lambda and v, top form would be lambda and v star. Then f star t acting on v, top vector, would be t acting on f of v, which would be t, well, because v is a top vector, f of v is by definition determinant of f acting on v, which is determinant of f times t acting on v. So f star t is always determinant of f times t. Right. Definition of the wedge product None of the chalks are long enough. Also known as the exterior product. So if alpha and beta are two forms, we define alpha wedge beta as p plus q factorial divided by p factorial, q factorial, and the alternation map acting on alpha tensor beta. And this is an element of lambda p plus q p. All right. As far as I know, different references use different conventions for these factorials outside. So we just, hmm? I've seen different ones.
Doesn't it have to be that it's just based on the no, like dx dy has to be dx dy right now.
Dx dy what?
Like when they're both first degree one.
Mm-hmm.
You can check that.
Oh, okay.
Shouldn't give any weird factors like one half and stuff.
Okay. All right. Because I've definitely seen different conventions for this, but whatever.
I mean, this is the one that makes
Most sense. Yeah.
just all the number of ways you're going to when you do this alternation, the number of combinations.
Yeah, exactly.
It's like
Exactly.
you divide in the factorials to make them normalized as tensors, and then you multiply it by proper factorial.
Yeah.
Basically, it's a
That-
question of whether dx wedge dy equals dx dy minus dy dx,
or half of that. Yep. So some properties of the wedge products. Alpha wedge beta is equal. Yeah. So alpha wedge beta is going to be. So if alpha and beta aren't forms, then you can still define the wedge product on them by just converting them into forms. Pretty trivial. Wedge is a bilinear product with alpha wedge beta equal to -1 to the degree of alpha times degree of beta times beta wedge alpha. 3, associativity. Maybe it would have been just quicker to write the formula. If you have alpha 1 wedge dot 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 alpha k acting on a bunch of vectors v1 where to vk, well, where these are all elements of lambda 1 v, each of these, and similarly these are all elements of v. This is going to be equal to determinant of alpha 1 acting on v1 dot 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 alpha 1 vk alpha k v1 alpha k vk. I don't want to. Too many indices. There's not enough time. It's not enough time. It's not enough time. All right, let me just write the fifth proposition.
If we define this as an algebra, or if we set this as an algebra,
Mm-hmm. A wedge B is A tensor B minus B tensor A over 2. Yeah. Yeah, that's just that. Yeah. I mean, one forms are just all the covectors anyway, so. All right. 5 for alpha, beta, 2 arbitrary differential exterior forms, and a linear map f from v prime into v, f star of alpha wedge beta is going to be f star alpha wedge F star beta. Hmm? But, yeah. So just trivially true. Yeah. Every like as long as it's defined linearly with respect to the tensor product. All right. So the proof of the determinant stuff. Oh, is that?
Let me do it. You can have your office hour and stuff.
Yes. Thanks. Bye.
Yeah. This is a lot of fun. Let's have fun. So we need to compute the determinant of f, right? What's the determinant of f? Well, we have a basis for this vector space, which consists of one vector, right? So obviously I'm going to choose, so I say this is span of E1, wedge, all of these guys, En, right? And so determinant of f equals, is defined this way. I just need to take f star and act on this vector, right? Sorry, not f, just f, tensor k if you wish, on, yeah, okay. So lambda n of f applied to this vector is going to be equal to determinant f times that vector. That's my definition of determinant f. Right, now let's compute this explicitly by applying f to the e's. Right, so this equals, this wedge product equals k factorial alternation of the tensor product. Right, so this is f tensor k applied to E1, yeah, and then alternation, right? I can put alternation on either side of f. Then this equals k factorial alternation. F tensor k acts on this, of course, by just applying f to every e. And that's going to be, okay, I'll just write that. Oops. F of En. Now, these guys, we can expand using the matrix of F(A). So k factorial alt, and then we've got A1, I1, E I1, right? Tensor A I N N E I N, right? With Einstein summation. Huh? So these are, A's are all numbers, right? So I can just pull them up. K factorial A1, A N I N alt E I1 E I N. Okay. Now this alternation is a sum over some permutations, right? So this is going to be a sum over permutations of n elements of A1 so let's see how this works. So this object yeah, but I don't want to. I'm scared of trying that.
because that's not what I did in the notes. What?
Because we have sum over indices, sum over permutations of times all times k factorial times the alternation of that tensor, but the alternation is independent of our permutation indices, right?
Yeah, of course.
Except for sign factor.
So it's E of sigma of I1 E sigma of IN, and then sine sigma, right?
Wait, the alternating.
So is it really correct to write the second line because that alternation involves a sum over indices? So the alt contains data about these indices I, and you pulled the numbers out past the left, right?
No, it doesn't. Well, I mean, why?
Alternation by definition is 1 over k factorial sine the permutation.
These are not indices. These are numbers of these vectors in the basis, right? These are not like vector indices or anything. Yeah.
So here, so we have alt of that, right?
What?
So we have alt of that tensor product because the alt of the tensor is a n form or a form.
What are you trying to say? Are you trying to go in the opposite direction? Okay. Okay, what I want to do now is get rid of the sigma on these INs and move it over to the A, right? So basically, let's rename, let's, so basically I can shift the permutation in such a way that I'm varying these lower indices of A, right? But the up indices are just 1 through n, and this is 1 through n.
This is because you're summing over all permutations, so you can do that. So you're going to hit every.
Right. So let me write, I want to write this. Sine phi, and then A pi of 1, pi of n. So I'll do this in 2 steps. J1, Jn. EJ1 again. Okay, so now I just moved the permutation over to the lower indices of A. This should be obvious, right? This is just switching the order of the terms in the sum in such a way that this is yeah.
JK is sigma by K, and then put them all into the A's, and then relabel the A's.
Right.
Sigmas.
Yeah. Okay, and now I'm going to get rid of these permutations. Okay, so I'm going to add an extra sum over an extra permutation that encodes these guys in terms of 1 through n. Okay, so this will be equal to a sum over 2 permutations, sigma and pi, sine of sigma pi, so the product of sines, and then a 1 pi of 1, a n pi of n, e sigma of 1, e sigma of n. Right. But now the sum over so sine pi. So the sum over this is just alt of e's, right? So we get back the vector that we started. So this is e1 wedge en times the sum over only pi of sine pi. And so this is the determinant of A. Right. A question for those who were sleeping. If I switch the ordering on my basis, why doesn't the sign of the determinant break? like usually I switch some columns and like 2 columns in the matrix that changes the sign. That would be a problem for this definition.
You said it's isomorphism.
So.
So its column, its rows are also determined by choice of bases, right?
So
So that will show up, right, in your sum of permutations.
If you transpose two of your bases, E1 and E2, then you're also transposing two of the A's here, right? So the compensating sign is from the sine sigma sine phi thing, right? Because both of them, you're switching two things.
yeah, so I'm switching 2 rows and 2 columns at the same time, right? So that doesn't change the sign of the determinant. Okay, so this doesn't actually depend on the choice of orientation, which is good. If I were trying to define the determinant of a mapping between 2 different vector spaces, which we're going to do later, then you would need to have to define 2 orientations on those 2 vector spaces first. Okay. I guess that's it. So the determinant is just the nth exterior power of the linear map. Now you know.